today I'm going to tell you about building new biological objects. I do that over in Pasadena at the California Institute of Technology. We build new things that will hopefully solve some human problems. But the way you can think about this is we're going to program living organisms. I'm going to make them do what I want them to do by treating them like little robots. These are your killer robots that you're worried about. The problem is that we have to implement this in really sticky, gooey stuff like proteins. It's not silicon, it's not steel, it's proteins. We don't really understand how this stuff works. And it's particularly tough to design something that you really don't understand. So I'm going to tell you, how do you build something that you don't understand? These molecules do amazing things. They carry stuff back and forth, they catalyze reactions, and they're doing things that we don't know how to write down from first principles. However, the great thing is, it's all encoded in this really dull 4-letter alphabet. That's the stuff of life, the code of life, the DNA. So this genome, which you may have heard quite a bit about, is something that we can chemically synthesize now. This is so awesome. You can go and you can order, you can send an email order off to a company in Northern California and they will FedEx genetic material back to you as long as it's not smallpox. You can stick this into a living cell. You probably saw this on the cover of various magazines just a couple weeks ago. Craig Venter synthesized 1 million base pairs of DNA, stuck it into a bacterium where they'd taken it out, and it started self-replicating. It's really boring to make something replicate. What we really want to do is make bacteria that will solve problems for us. And the problem here is that even though we can write anything, we've got this beautiful piano that you can play, but you don't have any music for it. We don't understand what sequence of DNA encodes a useful function. So what do? If you don't understand, in life, details matter, right? 1 minute you're dead, 1 minute you weren't. It's all in the details that makes a big difference. But there's an algorithm. So in no other human engineering system is there something like this called evolution that takes care of all the details for you. And we know that from looking at sequences of molecules that you can find just basically off the bottom of your shoe and comparing those sequences, that it all came about by this process of random mutation and selection, which I do in the laboratory across the Great Divide. And we can introduce mutations into DNA just by copying it under error-prone conditions. Most of those mutations are deleterious and get thrown away. But if you ask the right kind of questions, you can breed molecules just like you breed cats and dogs. Now, at this point in the talk, though, you should be thinking about the previous talk, because that's not the only search algorithm that works for design. Oh, by the way, I should tell you, this is really good, not just for making molecules, but for evolving, all levels of complexity in biology. One algorithm fits all. Where else do you find something like that? But go back to this other talk. Really got me very excited, because sex is one of the most important evolutionary mechanisms for discovering interesting new things. Now, in my experience, I can throw a lot of the children away. You guys can't do that. But and also in my experiments, I can do this all by mail, so I don't have to worry about encountering, the encounter probabilities for worms and monkeys and plants, and I can breed them all together at once. And so I can make genes with pieces from all these different organisms and explore the sorts of really interesting functions that they have. When you put 2 cats together, you usually get functional cats. In my experiments, because I'm now mixing cats and everything else, it's not necessarily anything that you'll get functional. So one of my problems is to sit around and figure out, how do you have a chance of actually making something useful out of these experiments? So we figure out what are the Lego blocks that makes up these molecules. And it's kind of a fun way to spend your time if you can't do all the things that Felice was telling us about. So what are the sorts of things that we work on? I'll just leave you with one example. We'd love to be able to use renewable resources in order to drive our cars and to replace all that stuff that's pouring into the Gulf of Mexico. And so we're building organisms and training them and evolving them into things that can make oil for us, for example. So that's the kind of problem that we hope to be able to solve with this technology. In fact, there's quite a bit going on. So I'll just leave you with this thought. These little killer robots, well, you can train them to be very useful, and they will work for glucose, and there'll be billions of them in a little liter. So they're all working, trying to solve your problem, and evolution is the algorithm that makes it work for you. So Thank you. And